I can change that. So the day one was the asymptotes lesson.
Yeah. Can we just do that again?
No.
Yeah, wait.
Okay, so what is an exponential function? An exponential function is when your exponent is the variable. So an exponential function is when your variable is the exponent. So an example would be f of x equals b raised to the x, where b has to be greater than 0. Why am I saying b has to be greater than 0? So our base has to be greater than 0. Why do you think that? What happens if b is less than 0? What could potentially happen there if b is less than 0? So if our base is less than 0. Aditya?
B was 0, would it become undefined?
Well, no, that's only undefined if b is like in the denominator. So that's okay. We're just talking about why does b have to be greater than 0? No? Okay, think of numbers that are less than 0. What about negatives? Exactly. So if we're talking about negatives, what happens there? Let's say I have -1, right? But then I raise it to the half power. What happens there? What does that end up being? An imaginary number. So we're doing this to avoid imaginary numbers. And if b is equal to 0, 0 to any power is just still 0. So it's not really giving us anything. So let's write that out for you. Must be greater than 0 because if b is less than 0, we have the potential of getting imaginary solutions. So an example would be y is equal to -2 raised to the x power. If x is equal to 1, 2, 3, and so on, we're okay. But what happens if x is a half? It doesn't work out, right? If x is equal to a half, we end up getting an imaginary number. Okay, so now let's talk about if b is greater than 1. If b is greater than 1, the function is increasing. And we always read a graph from left to right, because in America we read from left to right. So if the function is increasing, that means from left to right we're going up. And when your exponent is in, when your variable is in the exponent, what does this tell us? This thing is going to grow slowly, or is it going to grow very quickly? It's going to either grow, it's going to either increase or decrease at a very, very rapid pace. because now it's negative, let's say, well, not -2, but let's say our base is like 2. You're going 2 to the first, but then all of a sudden 2 to the third, right? Aren't you jumping big numbers when you're changing your exponent? So it's going to be growing very rapidly. So let's talk about f of x is equal to 2 to the x. Can 2 to the x ever equal 0? Is that possible? Is there any number we can substitute in for x that will ever yield us a 0? No. What does that mean? If 2 to the x can never equal 0, what does that mean for us? For our graph. If 2 to the x can never equal 0. Matt? There's no y-intercept.
No.
Never touch.
Doesn't touch the origin.
It won't, that's right, this one won't touch the origin. What else won't it touch?
The x-axis.
The x-axis, right? If 2 to the x can never equal 0, what does that mean? It's saying, right, y equals 2 to the x, so therefore y can never equal 0. So what does that mean? The x-axis is what? What does the x-axis act for us? An asymptote. The x-axis acts like an asymptote to us because our function can never cross that x-axis because it will never equal 0. There's no value that we could plug in for x that will ever make it 0. So we know that much, right? All right, let's see what happens here. Let's just make a chart, even though in the future we will not be making charts. All right, so our function is y equals 2 to the x. Let's just plug in random x values. I'm going to start with -2. All right, could our exponent be negative? Absolutely. Can our base be negative? No. So we're going to say, what is our y? So our y will equal 2 raised to the -2nd power, which is the same as 1 over 2 squared, which is 1/4. All right, then let's substitute in -1. So now we're going to have y is equal to 2 to the -1st power, which is 1 over 2. Then let's have 0. Y will equal 2 to the 0 power. Well, anything to the 0 power is always 1. Now let's substitute in 1. Y equals 2 to the 1st power, which is 2. And last one I'm going to substitute in now is +2. Y equals 2 to the 2nd power, which is 4. All right, so now let me get some graph paper here. All right, so now we're going to sketch this. And because 2 to the x can never equal 0, we have asymptote at y equals 0, which is the x-axis. All right, let's plot these points. So we are at -2 1/4. So I'm going over -2 and up just a little bit. It's an estimate. And then we have -1 1/2. So over -1, up 1/2. Then we have 0 1. And then we have 1 2. And then we have 2 4. And we know the x-axis acts as an asymptote, so we're looking something like that. All right, you all tell me, what is the domain here? Good. The domain is all real numbers. What about the range?
Everything greater than y equals 0.
You got it. Y such that y is greater than 0. Is it equal to 0? No, it can't equal 0. Okay, so we know if our base is greater than 1, our function, our graph is increasing. Can I just say when our base is less than 1 for the next one? No, I can't just say it's less than 1. Why? Because it can't be less than what number? 0. So now we're going to talk about what happens when our base is greater than 0 but less than 1. So what am I really talking about? Positive fractions, right? When our base is a positive fraction. So let's look at y equals a half x. Can a half raised to the x power ever equal 0? Is it possible? Is there a number that we could substitute in for x that will make a half 0? No. So what does that mean? What does that mean for us? If there's no number that we could plug in for x that will make it equal 0, that means y will never equal 0. So what does that mean for us? Again, once again, 3 little dots means therefore asymptote at y equals 0, which is the x-axis. Right, I'm going to make a little table again, even though in the future we will not be making tables. We have x, we have y. I'm going to substitute in the same numbers I did last time. So I'm starting off with -2. So we know y is equal to a half raised to the x power, which means we're going to do a half raised to the -2nd power, which brings us to what? 2 squared, which is 4. You got it. Then we'll go on to -1. So I have y is equal to a half raised to the -1st power, which just gives us 2. Then we're going on to 0. Y is equal to a half raised to the 0 power. Anything to the 0 power is always 1. And then x is equal to 1, so we have a half raised to the 1st power, which is just a half. And the last one we're going to plug in is y is equal to a half raised to the 2nd power, which is 1/4. All right, so let's sketch this. All right, so we are at -2, 4. 1, 2, 1, 2, 1, 2, 3, 4. And then we are at -1, 2. And then we're at 0, 1. And we are at 1/2. And then 2, 1/4. And then don't we know that we have an asymptote on the x-axis? So it looks something like this. So now look at our function. Are we increasing or decreasing? We always read from left to right. This is decreasing. What does this tell us? It tells us if our base is between 0 and 1, we are decreasing. All right, some vocab we need to know. Key point. Right. The parent graph of any exponential function crosses the y-axis at the point 0, 1. Why does this make sense? Why, when we're dealing with an exponential, y equals b raised to the x power, that's like what our parent function is, some number raised to the x power. Why? Why am I always going to cross the x-axis at the point 0, 1? David?
Anytime you raise a number to the 0 power, we equals 1.
Good, because any time we raise a number to the 0 power, we end up yielding a 1, right? So if I raise any base b and put in an x for 0, put in a 0 for x, any number that I put in for b raised to the 0 power will always give us 1. That's why we'll always, for a parent, something that looks like this, y equals some number raised to a power, will always have that key point at 0, 1. I'll write that out for you. Because anything raised to the 0 power is always 1. This can change if there is a number in front of the base. I'll show you what I mean by that in a second. All right, something else we should know. There is always a horizontal asymptote one unit below the key point, except if the base is except if there is a number in front of the base. Let's write that. Except if there is a number in front of the base. And I'll give you an example now. Let you write it down. All right, so let me show you this little exception here. So if I have y is equal to 2 times the quantity of a half raised to the x power. So now things are changing here. So I'm not going to have a key point at 0, 1 anymore, because when I plug in a 0 here, yeah, this quantity changes to 1, right? A half to the 0 power is 1, but then what am I doing? Multiplying it by 2. So that whole rule where there's always a key point at 0, 1, and there's always a horizontal asymptote 1 unit below the key point, that can change. That can change if we put different numbers. So what would this look like? Let's just play around with some points. If x is 0, then y is what number? 2. So now my key point is 0, 2, not 0, 1. Do we still have an asymptote at y equals 0? No? Is there anything I can put in here that will make this 0? There's nothing that I can put in here that will make this 0. So is there still an asymptote at y equals 0? Yeah. And now, is this function increasing or decreasing? It's decreasing because our base is a fraction, right? So this looks something like that if we're just doing a quick sketch.
So the key point is wherever x equals 0?
Yes. Okay, let's talk about when the base is e. All right, so the base e is an irrational number that is equivalent to 2.718. And it goes on. It's irrational, so it keeps going on forever. Keeps going. But we're estimating it to 2.718. Yeah. So now this is defined by the limit as n approaches infinity of 1 plus 1 over n raised to the n power. So what they mean by the limit as n approaches infinity, what happens as when we plug in numbers for n and they keep getting bigger and bigger and bigger and bigger and bigger, obviously numbers never stop. That's why we're saying approaching infinity, meaning we're approaching the positive side to infinity. Our numbers just keep getting larger and larger and larger. So who has a calculator here? Okay, take out your calculator, plug in this for us. So we're going to plug in numbers for 10, just so I can show you. Numbers for n. Let's start off small. Let's start off for 10. So you're going to do in your calculator parenthesis 1 plus 1 over 10, close your parenthesis, raised to the 10 power. And then what should we be? 2.593? Okay. So now let's get bigger. Let's do 100. So we are 1 plus 1 over 100, close your parenthesis, raised to the 100th power. What is that? 2.71, no, 2.704. Okay. What's happening? As we're getting bigger, doesn't it look like we're getting closer to this? All right, let's plug in a bigger number. Let's do 1,000. So this is 1 plus 1 over 1,000 raised to the 1,000th power. What's that? 2.716. Again, what's happening? We're getting closer, right? So now let's do 100,000. So you're 1 plus 1 over 100,000 raised to the 100,000th power. Are we 2.718? No? Yes? No? Maybe? And then, just for fun, yeah, do like a crazy amount of zeros. Well, you don't have to, but if we do a crazy amount of zeros, you're still going to be 2.718. It's just the decimals are going to keep changing after that. So what is this saying? as you get, as your limit approaches infinity, this is where we're heading. So the bigger you get, this is where we're at. Okay, so let's talk about y equals e raised to the x. So what have we learned? We've learned that e is a real number. So doesn't this follow all the rules that we just talked about? So it's really all the same. If I put a base of 2 or a base of e, it's going to look very similar. It's just a real number that's greater than 1 raised to the x power. So what does this look like? This looks like key point 0, 1. X-axis is our asymptote, and we are increasing. I want to show you on Desmos, but I don't want to lose the screen. If I move away from the screen, will it keep recording, do you think?
Maybe you do 2 different recordings.
All right, let's see what happens.
Oh no, it's still recorded.
Okay. So just to show you, graphing calculator, y equals 2 raised to the x. All right, that's our exponential. We have our 0, 1 as our turning, our key point, right? Now let's do y equals e raised to the x. All right, same idea, right? Asymptote key point is still 0, 1. No matter what number I make that base, let's do y equals 4 raised to the x power. All right, do you notice we're still following that same trend? Okay. And what's going to happen if I were to make that base not a negative, a fraction, a half raised to the x power? Now it's the same idea, but what's happening? We are decreasing. All right. So just wanted to show you. Let's go back here. All right. If we did 1 over e, same idea. What would happen? Let's go back. Just decreasing. Okay, so now we're going to talk about logs. Actually, we're not going to talk about logs just yet. Let's talk about translating our exponential functions. So let's talk about translations now. So let's say I have y is equal to b raised to the x minus h plus k. Based on all the other graphing we have done before, what do you think h and k represent? Horizontal shift and vertical shift. So h represents the horizontal shift. And k will represent our vertical shift. And what am I shifting, if you had to take a guess, when I'm saying shifting our horizontal and our vertical? The key point. There's no real vertex here. We're shifting our key point, exactly. So and our key point from what? Our parent graph. In our parent graph, the key point is always 0, 1, right? Always looks something like that. Or like that.
Is there anything in front of B? Like, could you put A in front of B?
We can. For our purpose, we're not going to, but I needed to show you that in the beginning that things can change. All right, let's look at this. if I have f of x equals 2 to the x and then minus 1. What does that tell us? That tells us I have my parent function, so I have my parent function would be y equals, I don't know, 2 to the x, right? And my key point for my parent function is 0, 1. And we have an asymptote at the x-axis. Am I increasing or decreasing for my parent function? Increasing. So do we all agree it looks something like that? All right, but now what's happening? I'm taking my parent function and now I'm shifting my key point. Where am I shifting my key point? 1 unit down. So instead of 0, 1, I'm now going to be 0, 0. And now there's always a horizontal asymptote where? 1 unit below the key point. So now I'm going to have a horizontal asymptote here. Are we still increasing? Absolutely. So what does this graph look like? Something like that. My pink one. Right, so let's talk about f of x equals 2 to the x minus 1. What is my key point?
0, 0.
Key point is 0, 0. What is my asymptote?
X equals -1.
X equals -1?
Oh,
Why?
Y equals -1. What is my domain?
I see. All real numbers.
Our domain is all real numbers. You got it. What about our range? Y such that y is greater than -1. You got it. Do we have this? Okay. I want you guys to try this one on your own. I want you to sketch y is equal to 2 raised to the x minus 3 power. All right, so we're going to look at our parent function. Our parent function here would be y equals 2 to the x, where we have our key point at 0, 1, an asymptote at the x-axis. But now what's happening? I'm shifting this key point 3 units where? To the right. How come it's not to the left? Because it's supposed to be x minus h, right? So now we're shifting 3 to the right. 1, 2, 3. So now we're here, and we're still going to have an asymptote 1 unit below it. So we're still have an asymptote at the x-axis. Now, to be a little bit more accurate, guess what I'm going to ask you to find? Yeah, to be a little bit more accurate, I'm going to ask you to find the y-intercept. So the y-intercept is going to be y equals 2 to the 0 minus 3 power. So y equals 2 to the negative third power. What's 2 to the negative third power? You got it. So our y-intercept is 0, 1/8, which we know will be pretty close to the x-axis. So what is it looking like? We are looking like this, something like that. Y equals 2 raised to the x minus 3 power. Yep. All right. We have to make a connection here. So let's look at y equals b to the negative x power. Do we agree y equals b to the negative x power is the same as 1 over b raised to the x power? All right, so if I were to give you y equals 1 over b to the negative x power, we can just change this to what? B to the x power. And what if I have y equals negative b to the x power and y equals the negation of b to the x power? Are these the same or different, what I just wrote here? This is like Algebra 1, biggest mistake.
They're different.
You think they're different?
Yeah, I agree with Dylan.
No, they're the same.
So according to order of operations, let's look at this. According to order of operations, do we all agree this is a -1 here? Yeah. So don't I have to do b to the x first and then multiply it by -1?
Yeah.
Isn't that what this is saying to do? B to the x, then multiply it by -1. So are these the same or different? These are the same. What's different? If I did the negation of b to the x and negative b raised to the x, these are different. Do we see the difference here?
Yeah, that's gonna mess up.
Don't mess up. So then let's talk about what y equals the negation of b to the x is. Does anybody know what this is on the graph? So it's b to the x, and then what are we doing to it? That negation in the front. Any guesses?
Oh, is it
Flip it.
We're flipping it over what?
the x-axis?
Y-axis.
The x-axis. We're flipping it over the x-axis. This is...
It's like a reflection.
It's gonna be like this.
What?
No, it's not.
Oh, wait, no, it's not the x-axis. It's a reflection of
Oh my god. That's the point.
y, yeah, y equals b to the x.
That's a bet.
You got it.
That's what it is.
All right, let's look. I'm going to show you. Which is like the x-axis.
Alright, almost done.
No. This will probably take 2 days.
Oh.
Okay. So this is a reflection. Let's do one. Y equals the negation of 3 to the x, and y equals 3 to the x. I actually want to show you this on Desmos. Yeah, we don't have to graph it. I just want to show you on Desmos. So we have y equals 3 raised to the x, and then y equals the negation of 3 to the x. Oh, what happened there? Oh, I'm like, that's not right. There we go. So we're just taking it and we're reflecting it over the x-axis, so it's just a reflection of the original. All right, so why am I doing this? Let me show you something a little bit more complicated. So write this down, reflection. It was just a reflection over x-axis. So now I want us to sketch y equals the absolute value of 3 to the x minus 2. We've dealt with absolute values before. What does it mean when we have an absolute value? It doesn't mean we're graphing the v, right? Because what's inside of it is not a v. Right? This is saying graph this exponential and then do what to it? After we graph the exponential, take the absolute value of it, which means what?
Positives only.
Positives only. You got it. All right. So let's sketch. I'm only going to sketch what's inside my absolute value sign first. So I have y equals 3 to the x minus 2. My key point for my parent function is 0, 1. But what am I doing to that key point? I'm shifting it where? 2 units down. Are we okay so far with this? Shifting it, the key point 2 units down. And then what should be 1 unit below that key point? A horizontal asymptote. Do we agree this is going to look something like, actually, guess what I'm going to ask you to find now? I'm going to ask you to find the x-intercept. Yeah, let's find the x-intercept here. So we have y equals 3 to the x minus 2. Oh, you know what? Don't worry about the x-intercept right now. We'll deal with that later. All right, so we're just sketching. Let's do this. So do we agree it looks something like this? Yeah? All right. So now what's going to happen? What's going to happen now is I need to take the absolute value of this. So what's our problem? Our problem is everything I'm highlighting in yellow. This whole area is the problem because y has to be greater than 0, right, for it to be absolute value. So all we're going to do is just sort of reflect that 1 point. So instead of 0, negative 1, we are at 0, 1, 0, positive 1. We're taking the absolute value of it. So now we are here. And now there was a horizontal asymptote at, what was this, y equals negative 2? So now I'm going to put a horizontal asymptote at y equals positive 2. Can we cross a horizontal asymptote? Absolutely, we can cross it. So is that okay that this is crossing it? Absolutely. So the horizontal asymptote is sort of just giving us an idea of what it's going to look like. So what happens here? It looks like it's going to be hug, 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 down. So then all this gets erased.
Are those points supposed to like touch? Those 2 lines?
Which 2 lines?
Like those 2 separate lines, like the one in blue and then the one in
Yes,
green.
this is all connected.
Okay.
So it's all one right there. Yep, that's all one. I'm saying do number 6, 9, and 10 from worksheet. What are those? I think we can stop here. We still have a whole nother day worth of lessons, so I think we can stop here.
I'm on the last page.
My second.
I'm on my third.
Yeah, I'm on my third too.